If I say the word, or rather the acronym RADAR, you'll probably imagine something like this. However, if you drive on the UK's network of newly implemented smart motorways, you're being surveilled by a very different radar, and it's closely watching your every move. It knows where you are, it knows the second you move, and it knows exactly when you stop. But to explain this, let's go back a few years to the other side of the world and look at a company called Navtech and their involvement in using radar at ports. The roots of Navtech systems stem from Philip Avery's involvement with millimetre wave radar, which started in 1992. Systems were originally developed as navigation sensors for container handling vehicles in stevedoring applications. The technology was used in 1993 to successfully demonstrate the first automated port vehicle to use millimetre wave radar. In 1996, Dr. Stephen Clarke started further research into the uses of millimetre wave radar at the Australian Centre for Field Robotics in Sydney. Philip Avery joined him there, and in 1997 they worked together on turning a working prototype into a reliable industrial sensor. In 1999, Navtech Electronics was formed in the UK, and this is an example of an early FMCW radar, or frequency modulated continuous wave radar, from 1999, which kicked off the automated port project in Australia. Now, if you're still wondering what this has to do with smart motorways, then bear with me. This project wasn't born from the continual drive of technology companies to better improve systems, but rather an event that started a year earlier in 1998. The Australian waterfront dispute in that year was an event in Australian industrial relations history, in which the Patrick Corporation undertook a restructuring of their operations for the purpose of dismissing their workforce. Major events in the dispute occurred in 4 major ports where the Patrick Corporation had significant operations, and these were Melbourne, Brisbane, Fremantle and Sydney, and all of this led to the requirement of an automated transport system for containers moving around these ports. So fast forward a few years to December 2005 and the opening of the Patrick Corporation's $106 million Autostrad terminal at Fisherman Islands in Brisbane. This was Australia's first automated container terminal. The automated 10-metre high 65-tonne straddle carriers, which are called Autostrads, were fitted with Navtech FMCW 77 GHz radars as an integral part of sophisticated motion control and navigation systems. This allowed them to operate unmanned, moving and stacking containers from the quay into holding yards, onto vehicles and back to quay cranes with pinpoint accuracy as the world's first free-ranging automated straddle system. So how does it work? Well, I've been showing you a lot of pictures of these Autostrad systems, and if you look closely, the white dot on the Autostrad is the 77 GHz radar. At set points around the port are radar navigation targets known as corner reflectors, and you can see them mounted on brackets on these posts. A corner reflector consists of 3 mutually perpendicular intersecting flat surfaces which reflect waves directly towards the source. The incoming ray is reflected 3 times, once by each surface, which results in a reversal of direction. Radar corner reflectors are designed to reflect the microwave radio waves emitted by radar sets back towards the radar antenna. A simple corner reflector consists of 3 conducting sheet metal or screen surfaces at 90-degree angles to each other, attached to one another at the edges, forming a corner. These reflect radio waves coming from in front of them back parallel to the incoming beam. To create a corner reflector that will reflect radar waves coming from any direction, 8 corner reflectors are placed back to back in an octahedron or diamond shape. So, in simple terms, an autostrad is moving around the port carrying a container. On that autostrad is the 77 GHz radar, which is constantly transmitting. The signal is reflected back towards the radar from the corner reflectors from all directions. These reflections are then processed by a computer to provide reliable and accurate absolute measurements to the series of pre-surveyed target reflectors in the operating environment. Therefore, in simple terms, the autostrad knows exactly where it is. Amazingly, the accuracy is within plus or minus 25 millimeters over a range of 200 meters. Now, this isn't coincidental either. The accuracy means that the autostrad can stack containers together using their interlocking mechanisms without danger. There are numerous fail-safes and backup systems to ensure the safety and accuracy of the autostrads, and one of them is GPS. So you may be asking, why not just use GPS? Well, GPS wasn't made for civilian use. It was designed and implemented for military use. For that reason, GPS is deliberately made less accurate for civilian use. It can be made more accurate by having a fixed local GPS receiver, for example on the roof of a building. A local radio network on the building broadcasts GPS correction information out across the surrounding area to mobile devices and vehicles. The GPS receive on the vehicle and the locally broadcast GPS correction information makes the vehicle's GPS positional information a lot more accurate. This is used in farming where tractors with GPS do the very same thing, but usually they have a fixed GPS receiver on a tripod at the edge of the field. So along with the inaccuracy, GPS also has other issues. It can suffer from multipath effects, for example reflections from the stacks of shipping containers which can cause inaccurate positional data. When an autostrad is under a container crane or other infrastructure, it may have a limited view of the sky, meaning it can't see a GPS satellite, leading it to lose GPS positioning. Using radar on top of an autostrad means that the radar itself can always see a number of radar navigation targets, even if the GPS can't see the sky, and this is an advantage of radar over just GPS navigation, and the reason why the autostrads utilise both. So again, what does all this have to do with smart motorways? Well, if you use the UK's network of smart motorways, you may have noticed these white domes at intervals along the side of the carriageway. These are Navtec 77 GHz radars, and not only are they very similar to the ones used on the autostrads, they could save your life. Navtec radar's millimetric wave systems were initially researched on the M42 to look into how this type of detector could assist in the opening of the hard shoulder as an additional running lane, which is essentially what the new smart motorways are. The hard shoulder acts as an additional lane. However, safety can't be compromised, and sitting broken down on a hard shoulder that could become active or in any lane is dangerous, and any decision on whether to open the hard shoulders to running traffic must be taken in the secure knowledge that they're clear of stopped vehicles or debris. Originally, the operational solution for the M42 used fixed cameras, which were placed every 100 to 200 metres along the route, which fed screens watched by the Highways Agency's traffic officers. Radar, however, was seen as much safer, accurate and most importantly effective when it came to automating the detection of stopped vehicles. The first proof of concept using a single gantry-mounted system to detect vehicles on the hard shoulder took place in 2007. A follow-on trial on the M42 involved a 3-radar system for detecting incidents across all lanes, and later a 5-radar system mounted typically 2 meters above the ground on existing adjacent gantries for the purpose of incident detection on the hard shoulder. The 5 radars in the latter test provided a total of around 3.5 kilometers of overlapping coverage. Navtec's 2 original products for the road monitoring sector were the TS500 and the TS350X. The TS500 can detect a man-sized object within a radius of 500 meters, which is a 1000 meter diameter, and a vehicle within a radius of 800 meters. The TS500 is suitable for mounting within a few meters of the road surface or at ground level. Higher mounting positions are feasible, but consideration has to be given to detection beneath the sensor's mount. The other model, the TS350X, can detect a man-sized object within a radius of 350 metres and a vehicle within a radius of 500 metres. This radar is suitable for mounting close to the road or on an elevated mounting and includes enhanced detection coverage. Although vehicles and vehicle incidents can be detected to 800 metres dependent on the sensor used, accurate determination of the lane in which the incident has occurred is only possible out to a radius of 300 to 400 metres. Where radar systems are concerned, the higher the frequency, the smaller the sensor required. This results in a compact system, which is why these radars are much smaller than something like a primary surveillance radar at an airport, which operate on much lower frequencies. A narrower beam also allows lane definition out to around 300 to 400 metres in either direction. So how does the smart motorway detect a stopped vehicle? Well, there are numerous sites across the UK which deploy Navtec smart vehicle detection, such as stretches of the M25, 3 road tunnels between Liverpool and the Wirral, the M62 between junction 20 and junction 25, and the Hindhead Tunnel on the A3. The radar sensors detect slow or stationary vehicles, as well as pedestrians and debris on roads or in tunnels, and in a wide variety of weather conditions. They're designed to cover 360 degrees and sample data at an angular resolution of approximately 0.4 degrees. Now, the radar antenna is designed to have a narrow beam width in azimuth. In this way, objects within the radar field of view can be accurately located on the road surface. So far as is possible, the radar has a wide beam in elevation. This allows objects close to the radar and far away to remain in the sensor field of view, even when it's mounted on a high gantry. The standard update rate for radar sensors is 120 RPM, which essentially means the radar inside the dome spins twice every second with a maximum detection distance of 500 metres radius. The system employs a frequency modulated sensor, and so, unlike Doppler systems, no movement is necessary to measure a vehicle, person or similar object within the radar line of sight. Now, the system that Navtec radars feed detects a stopped vehicle within 10 seconds of it coming to a standstill. The operator is then alerted and they can take the appropriate measures to make the situation as safe as possible. So that's an overview of the Navtec radar system that's constantly watching you on certain parts of the smart motorway network and one day could save your life.